We are going to be listening to Paul and Mark providing us some details on digging deep into the Flash sandboxes. So please go ahead and give them a round of applause and make them feel welcome. Good luck, guys.
Good afternoon. Thank you all for coming. I'm Paul and this is Mark. We're both from IBM's X-Force Advanced Research Team, and today we'll be talking about digging deep into the Flash sandboxes. In Blackhat last year, we gave a talk about Adobe's ReaderX sandbox, and in that talk we discussed the sandbox internals, its limitations and weaknesses, and possible avenues for sandbox escape. This year, we focused our sights on Flash sandboxes, and this time we had 3 different sandbox implementations to play with. When we started this research, we asked ourselves, as we did last year, some questions, and those questions are, what can an attacker or a malicious code still do even with the sandbox restrictions imposed? Another question is it still profitable for an attacker if he successfully exploited a system but could not escape the sandbox? And we were also interested to know which of the sandbox implementations is the strongest and which one is not as strong. And although not the main focus of the research we did, we were also curious if we could find some sandbox escape vulnerabilities. So what are our targets? These are our targets: the Flash Player Protected Mode for Firefox, Flash Player Protected Mode for Chrome, and Flash Player Protected Mode for Chrome Pepper. We will be referring to them as Firefox Flash, Chrome Flash, and Pepper Flash throughout this talk. These are all, by the way, the Windows versions of the software. Firefox Flash was first released as beta by Adobe last February of this year, and then released officially last month. It is developed in collaboration with Mozilla and Adobe, and the sandbox code is based on the sandbox code in Adobe's ReaderX, so there will be a lot of similarities between them. Chrome Flash, on the other hand, is the current default Flash player in Chrome, and is a result of a collaboration between Google and Adobe. It is meant to be a temporary solution just until the Chrome's next generation Flash Pepper, which is Flash player, which is Pepper Flash, is officially stable. We'll be talking about the version bundled with Chrome 20.0.132.47 in this talk. Pepper Flash is already, I'm not really sure, we're not really sure how many versions back, but it's already included in the current version of Chrome, but it is disabled, and you can enable it in the settings menu of Chrome. But a few weeks back, Google released Chrome 21 beta, and in that beta software, Pepper Flash is the default Flash player. So I think it's safe to assume that in the Chrome 21, the default Flash player will be Pepper Flash. So before we go deeper into the sandbox implementation, we will first discuss the sandbox architecture and the various components involved in the sandboxes. For Firefox Flash, we have the Firefox browser process, which is the process that starts when you first open Firefox, and the plugin container, and the Flash broker process, which is an instance of Flash Player plugin, and the Sandbox Flash plugin process, which is also an instance of Flash Player plugin, but Sandbox. You can see here some arrows connecting the various components. This indicates that at some point there will be some communication between them, and the labels are the kind of communication that will occur. This communication will be discussed in detail later by Mark. For one difference between Firefox Flash and the two other Flash implementations, that you can disable it via the MMSCFG configuration file, which is Firefox Flash's privacy and security settings configuration file. You can add this line, protected mode equals 0, in that in that mms.cfg configuration file to disable it. The mms.cfg configuration file can be found in the macromid/flash folder in the system directory. For Chrome Flash and Pepper Flash, since they're both running in Chrome, obviously there will be components that are common between the two of them, such as the Chrome browser process, which is the main browser process that is opened when you first run Chrome, and the Sandbox Chrome renderer process, which is the process for the page where you open the Flash content. In Chrome Flash, the Flash broker process is opened by running the plugin DLL Flash plugin DLL GC SWF32.dll's broker main entry point using run DLL32.exe. The Flash plugin process is an instance of Chrome.exe that loads the Flash plugin DLL GC SWF32.dll. For Pepper Flash, there is no separate broker process since the Chrome browser process will act as the broker process for this. As to why, that will be explained by Mark later. And the Pepper Flash plugin process is an instance of Chrome.exe that loads the PPAPI plugin ppflashplayer.dll. So now let's go deeper into the Flash sandboxes by discussing sandbox mechanism. Let's start with what happens when you first open a page with Flash content. For all three sandboxes, since they're all based in Chrome sandboxing code, they generally have the same startup sequence with some details, with some difference in some details that we will be discussing later in this talk. But in general, they all follow this sequence. First, the broker process will be started. Then the broker process sets up the sandbox restrictions. It sets up the integrity levels, the job levels, and the token levels. Then it will set up the policies. After this, the sandbox process will be spawned in a suspended state. And in this state, the broker process will set up interceptions inside the sandbox process. Interceptions will be discussed later by Mark. And once the interceptions are in place, the sandbox process will then resume execution, and that starts the parsing and rendering of the Flash content. Here's how the browser process tree will look like after a sandbox is started. You can see here the components that I've talked about earlier. For Firefox Flash, you can see the Firefox browser process, the plugin container, and the Flash player plugin.exe that spawned the Flash player, another instance of Flash player plugin.exe. You can tell that the last line is the sandboxed Flash player process, since the integrity level, this is the last row. This is actually Process Explorer's output, and the last row is the integrity level. And you can see here that it has an integrity level of low, and it's spawned by something that is a process that has an integrity level of medium, and this is the broker process. For Chrome Flash, you can see here that the Chrome browser process spawned run DLL32.exe that has a medium integrity level, and also Chrome.exe with a low integrity level. The run DLL32.exe is the broker process, and this Chrome process is actually the sandboxed Flash player plugin process. If you click in Process Explorer and look at the details, you can see that it loads the GC SWF32.dll. And the two other Chrome processes are just the renderer processes that happens to be open when I took the screenshot. For Pepper Flash, you can't really tell from this screenshot which one is the the sandbox process. But rest assured, one of them is. The two other, I think is this one. This is the last. The two other processes are just the render processes that happens to be open when I took a screenshot and when I opened the Flash content and took the screenshot.
We'll now talk about sandbox restrictions. These are the mechanisms used to restrict the capabilities of the sandbox Flash process. It uses 4 windows mechanism for the restrictions. They are the restricted tokens, integrity levels, and job objects, and alternate window and alternate desktop. So for the restricted tokens, as you can see, Flash has no enabled privileges. And if you look at the combination of deny-only seeds and restricting-only seeds, Flash has the most restrictive. And it is very difficult to find a resource that this restricted token can access. For Chrome Flash and Firefox Flash, the restricted token can still access resources accessible to the everyone and users group. In addition, in Chrome Flash, the restricted token can still access resources accessible by the user seed. This means that the restricted token can still access private users files located in the user's documents folder. For the integrity level, Flash runs as an untrusted, while Chrome and Firefox Flash runs as low integrity. This prevents write access to most secureable resources because most of the secureable resources in the Windows system have a medium or a higher integrity level. For job restrictions, Flash has the most job restrictions. Chrome Flash has the least. Unimportant job restrictions only found on Flash is access to the clipboard and global atoms. This is important because the clipboard and global atoms are potential vectors for sandbox escape and information disclosure. Finally, Flash is the only sandbox Flash that uses alternate window station and desktop. Firefox Flash compensates the lack of alternate desktop via the job restriction and running under low integrity. The next thing we will discuss is the interception manager. So what does the interception manager do? What it does is that it transparently forwards API calls from the sandbox process to the broker or the browser process. It is needed because there are cases where the sandbox process need access to some resources for compatibility reasons or for the proper functioning of the sandbox. Interceptions are done via API hooking. So these are some examples of API hooking. They have API hooking for NTDLL, and there is an example for API hooking which injects a junk code in the entry point of the API. And there's an example that there's a type that patches the export address table of the DLL. To visualize, to visualize in Chrome Flash, APIs are intercepted in the Flash plugin process, and they are forwarded to the Chrome browser process, where they are evaluated by the policy engine. In Flash, it is the same. The APIs are intercepted in the Flash plugin process and are forwarded to the Chrome browser process, and then evaluated by the policy engine. In Firefox Flash, is a different picture. The Flash plugin process APIs are intercepted in the Flash plugin process and sent to the Flash broker process, where they are evaluated by the policy engine. Now we will talk about the enterprise communication. In our research, we had found 3 IPC implementations being used: Sandbox IPC, Chromium IPC, and Simple IPC. Sandbox IPC is originally from the Chromium project. It is used by all Flash Sandbox implementation. Originally, it was used for forwarding API calls made by the Sandbox process to a higher privilege process. But in Firefox, It is also additionally used for invoking additional services exposed by the Firefox Flash Broker. To visualize, there's a Sandbox IPC connection between the Chrome browser process and the Flash plugin process, and this is used for forwarding API calls. In Pfefferflash, it is the same. There's a Sandbox IPC connection between the Chrome browser process and the Flash plugin process, and it is also used for forwarding API calls. In Firefox Flash, there's a Sandbox IPC connection between the Flash Broker process and the Flash plugin process. It is both used for forwarding API calls and for invoking additional services. Chromium, this is the second IPC implementation. Chromium IPC is original from the Chromium project and also used by all Flash Sandbox implementations. In an endpoint of a Chromium IPC connection, there are listener classes which handles the dispatching of the IPC message. To visualize, the Chrome browser process, the renderer process, and the Flash plugin process are all interconnected via Chromium IPC connection. In Pfefferflash, it is the same. The Chrome browser process, the renderer process, and the Flash plugin process are all interconnected via Chromium IPC connection. In Firefox Flash, the plugin container communicates with the Firefox browser process, the Flash Broker process, and the Flash plugin process via Chromium IPC connection. The last IPC implementation we'll discuss is the Simple IPC. Simple IPC is also developed by Google. It's developed by Google and hosted at the link on the screen. And it is only used in Chrome Flash and used for invoking services exposed by the Chrome Flash Broker. To visualize, there's a simple IPC connection between the Flash Broker process and the Flash plugin process, and it is used for invoking services exposed by the Flash Broker process. After discussing about the enterprise communication, we'll now discuss the services exposed by the different Flash Sandbox process. These services are invoked via the IPC mechanisms I previously discussed. A detailed list of services are in the companion white paper in your Blackhat CDs. So we will discuss 5 sets of services. The first set of services that we'll discuss is the Chrome Sandbox services. These are the services hosted in the Chrome browser process and which handles the forwarded APIs. It is invoked via Sandbox IPC, and service handlers in the Chrome browser process are actually methods of dispatcher classes. And each dispatcher class handles a subset of APIs. For example, the file system dispatcher handles file system related APIs, while the registry dispatcher handles registry related APIs. To visualize, so the Chrome Sandbox services are hosted by the Chrome browser process and are callable by the Flash plugin process, and it handles forwarded APIs. Same with Pfefferflash. The Chrome Sandbox services are callable from the Flash plugin process and handles forwarded APIs. So the second set of services we'll discuss is the services exposed by the Chrome browser process and the Chrome renderer process to out-of-process NP API and PP API plugins. These are invoked via Chromium IPC. In the Chromium source, you will notice that invoking these services involves instantiating message classes. In this case, this is the instantiation of the PP API message log plugin message class, and the resulting class instance is passed to a send method. So these are the services exposed by the Chrome browser to NP API plugins, such as Chrome Flash. So the services exposed by the Chrome browser are mostly for just sending plugin status or notification to the browser process, while the services exposed by the Chrome renderer does the heavy lifting, as it exposes the support services for NP API calls. To visualize, the Chrome browser process exposes services which are called by the Flash plugin process for sending status updates and notification to the Chrome browser process, while the Chrome renderer process exposes support services for NP API calls via this Chromium IPC channel. For privileged NP API calls, the Chrome renderer uses another set of services exposed by the Chrome browser via this Chromium IPC connection. And for PPAPI plugins, it is the same. The Chrome browser process exposes services for the Chrome renderer to send status or notification message to the browser process. Differently, the Chrome renderer does the heavy lifting as it exposes the PPAPI services. Since there's a lot of PPAPI functionality, each functionality is divided into interface proxies. These are examples of interface proxies. So there's an interface proxy for dialog services, and there are interface proxies for clipboard services, and there are proxy interface for video capture services. So the third set of services that we'll discuss is the services exposed. Also, this is the visualization of this. So as you can see, the Chrome browser process exposes services for the Flash plugin to send status or notification updates to the Chrome browser process, while this channel is being used for PPAPI calls. So for privileged PPAPI calls, the Chrome renderer process uses another set of services exposed by the Chrome browser process. So the third set of services we'll discuss is the services exposed by the Chrome Flash Broker process. These are callable by a simple IPC and are callable to the Sandbox Flash plugin. Example services are dialog services for open and save dialog box. There are file system services for brokering calls to specific Windows file system related APIs, and miscellaneous services such as launching the Flash Settings Manager. To visualize, so the Flash Broker process exposes the Chrome Flash Broker services to the Flash plugin process via a simple IPC connection here. The fourth set of services that we'll discuss is the services exposed by the Firefox plugin container. These services are mostly for invoking NP API call, for forwarding NP API calls. So to visualize, the plugin container exposes services to the Flash plugin process for forwarding API calls to the Firefox browser process. So it is mostly for forwarding API calls between the NP API calls between the browser process and the Flash plugin process. So the last set of services that we'll discuss are the services exposed by the Firefox Flash Broker process. The Firefox Flash Broker exposes services to two processes. The first one is the Flash plugin process and the plugin container. And the service that it exposes can be divided into three: Sandbox services for forwarded APIs, Flash services for additional services, and permission services. Sandbox and Flash services can be invoked by a Sandbox IPC, and this is exposed to the Flash plugin process. So these are some examples of the dispatchers in the Firefox Flash Broker. So there's a dispatcher for file system related APIs. So this is actually ported from Chromium. And then specific to Firefox Flash, and we also found in ReaderX are these two. One that handles forwarded WinINet APIs, and a dispatcher that handles miscellaneous services. In the case of Firefox Flash, it contains services such as launching the Flash Player Settings Manager. So the Flash Broker also exposes additional services to the plugin container. This is invoked by a Chromium IPC. As of Firefox 11.3, the services involves granting, denying the Sandbox process access to window handles. To visualize, the Flash Broker process exposes Sandbox and Flash services to the Flash plugin process which is callable by a sandbox IPC, and it also additionally exposes permission services to the plugin container, which is callable by a Chromium IPC connection.
Okay, so now let's discuss the policy engine. The policy engine is responsible for evaluating the forwarded API calls against sandbox policies. These policies allow the broker to specify exceptions to the default restrictions in the sandbox. These policy rules are whitelist rules that grant the sandbox-specific access to certain objects, overriding the default sandbox restrictions. The policy engine is the same for all three sandbox implementations because they're all based on Chrome sandbox code with some differences I'll mention later. To add policy rules, you can do this programmatically using the add rule function, which you can find in the Chromium source code. This function takes three parameters: a subsystem, which indicates the Windows subsystem the rules will apply to, and semantics, which indicates the permission, the kind of permission that will be applied, and pattern, which is a string expression that will be matched to the file name or registry name or whatever object's name, and if it matched, the policy will be applicable. So here's some examples of subsystems. This is just a small subset, and you can see there's a subsys files for file operations and subsys registry for registry operations. And below it is some examples of semantics or the permissions. And you can see there's files allow any that will give the sandbox process full access to files. And another example is reg allow any, which allows read and write access to a registry key. There are some subsystems and semantics that can be found only in Firefox Flash, but not in Chrome Flash and Pepper Flash, and vice versa. So here's some examples of an add rule call. This can be found. The first example can be found in Firefox Flash, and it basically gives the sandbox process full access to any file in the folder in the pattern argument. In this folder. The next example will give the sandbox process registry read and write access to any key that starts with a string. So the one difference between Firefox Flash and the two other sandboxes is that Firefox Flash allows custom policies to be created using a configuration file. This custom policy file is enabled or will be read by Firefox Flash only if protected mode broker whitelist config file option is set to 1 in mms.cfg. The policy file is named protected mode whitelist config.txt and is placed in the macromed/flash folder in the system directory. The custom policy rules take the following format: policy rule type, which is a subset of semantics and indicates the permission that will be applied, and an equal sign, and the pattern string, which is synonymous to the pattern argument in the add rule function call. So here's an example of a custom policy rule. This rule will allow Firefox Flash sandbox process to full access to any files in the logs folder in the C directory.
After discussing all the sandbox mechanism, we will now show how all the sandbox mechanisms are all connected together. For Chrome Flash, so the APIs are intercepted in the Flash plugin process and are forwarded to the Chrome browser process, which are then evaluated by the policy engine. And then for sending plugin status and notification message, the Flash plugin process uses the Chromium IPC connection to the Chrome browser process. For NP API calls, the Flash plugin process uses the Chromium IPC connection to the Chrome renderer process, which then serves the support services for NP API calls. For privileged NP API calls, the Chrome renderer process uses another set of services exposed by the Chrome browser process. Because the NP API interface is limited, as you can see, we need for Chrome Flash needed another another Flash broker process. Its services are callable to the Flash plugin process via a simple IPC. So for Pepper Flash, it is almost the same as a Chrome Flash. The only difference, one of the difference, is that this connection is used for PP API calls. And as you can notice, there is no need for there is no additional broker process. This is because the PP API interface is adequate for Pepper Flash. For Firefox Flash, APIs are intercepted in the Flash plugin process, then forwarded to the Flash broker process, which is then evaluated by the policy engine. This channel, in addition to serving forwarded APIs, is also for invoking additional Flash services. For NP API calls, the Flash plugin process uses this Chromium IPC channel. The plugin container then forwards the NP API calls to the Firefox browser process. Additionally, the Flash broker process exposes permission services to the plugin container, which is callable by a Chromium IPC.
Okay, so now that we're done with the sandbox internals, let's talk about the security aspects of the sandbox. First, let's talk about sandbox limitations. When discussing sandbox limitations, we generally ask this question: what can a malicious code do once it is running within a Flash sandbox? And the answer is not much, but enough. So why is that? First, there's a limitation in that file system read access is allowed in some of these implementations. For example, Firefox Flash allows read access to all files that are accessible from the user's account, because this process token still has access to some of these files. And on top of that, there's a hard-coded policy rule in Firefox Flash that allows read access to all files, and this is explicitly declared using the add rule function we discussed earlier. That add rule call has the subsystem parameter of subsys files, and semantics is files allow read only, and the pattern is an asterisk, therefore allowing the sandbox process full read access to all files. Chrome Flash also does this and allows read access to all files through its process token. On the other hand, Pepper Flash does not allow any read access of files at all. So this limitation could lead to sensitive files such as financial documents, source codes, or cookies to be stolen. Another limitation is registry read access. For Firefox Flash, it allows read access to registry keys that are accessible from the user's account, brought about by having a process token that still has access to some of these keys. And also, there's a hard-coded policy rule that allows read access to major registry hives. There's an add rule call in Firefox Flash with the following parameters. With subsystem is equal to subsys registry, semantics is reg allow read only, and pattern is equal to HT classes root, the name of the major registry hive, followed by an asterisk, by a wildcard. So this rule will effectively allow Firefox Flash sandbox process read access to this registry hive. For Chrome Flash also allows read access to major registry hives because of its process token. But Pepper Flash does not allow any read access of registry keys. So this limitation could lead to disclosure of system configuration information in the registry and potentially sensitive application data from the registry. Another important limitation is network access. Both Firefox Flash and Chrome Flash do not restrict network access. So you can create a server, or you can connect to a remote server from within the sandbox. However, Pepper Flash does not allow any sacrification, so this limitation, it does not have this limitation. This limitation could allow transfer of stolen information to a remote server, and it also allows attack of internal systems not normally accessible from the outside by using the exploited system as a pivot point. Another limitation for Firefox Flash is it has policy-allowed write access to certain files and folders. It contains default policy rules that grant the sandbox process write access to certain folders and files that are related to Flash. And some of these folders and files are also for third-party applications, such as some applications from Microsoft. This limitation could allow an attacker to have control over the behavior of Flash or another application. Another limitation is clipboard read and write access. Both Firefox Flash and Chrome Flash do not have clipboard access restrictions set in their job objects. Also, Firefox Flash provides clipboard services through its Sandbox clipboard dispatcher. And again, as usual, Pepper Flash does not allow clipboard access. This limitation could allow disclosure of possibly sensitive information such as passwords in a scenario where a user might use copy and paste to copy a password into another window. Finally, this limitation is applicable to all the three Flash Sandbox implementation. It's write access to FAT or FAT32 partitions. Since these partitions don't have any security descriptor, the Sandbox restrictions cannot be applied. So this limitation could give propagation capabilities to malicious code running inside the Flash Sandbox. For example, by dropping a malicious file into a FAT or FAT32 partition USB flash drive. So what have we learned in this section? We learned that limitations and weaknesses still exist, and these limitations makes it possible to carry out information theft. And lastly, Pepper Flash, out of all the three, Pepper Flash is the most restrictive.
We'll now discuss the different methods for sandbox escape. Most of the items discussed here does not only apply to the Flash sandboxes, but can also be applied to other sandboxes as well. So the first option for an attacker to conduct a sandbox escape is to exploit local EOPs, especially those that result in kernel mode code execution. With multiple interfaces still available to the sandbox process, such as Cisco system calls and device objects, exploiting local EOPs to escape the sandbox are an ideal way to escape the sandbox. Second method for a sandbox escape is via name object squatting. This method involves a process creating a malicious name object, which is trusted by a higher privilege process. The malicious process then sends by writing data to the malicious name object. The behavior of the higher privilege process can be controlled. The third one, one of the primary vectors for a sandbox escape is the IPC message parser, because most of the code runs in a privileged context, and the first code to touch untrusted data. Code that are interesting are the IPC message parser and the code that deserializes IPC call parameters, especially those that are complex. All IPC implementations we have discussed are open source and a source audit is possible. Policy vulnerabilities. Auditing for policy vulnerabilities involves looking for write aloud policies, and then identifying if the policy can be used to control the behavior of a higher privilege process. For example, for write aloud policies for registry key, does the registry key contain configuration entries used by higher privilege applications? For folders, does it contain executable files which you can overwrite, or does it also contain configuration data which you can modify and then control the behavior of the higher privileged application that uses it? Policy engine vulnerabilities are critical because the policy engine decides which potentially security sensitive action to allow or deny. An example of a policy engine vulnerability is the vulnerability we identified in Reader X last year, and we demoed the vulnerability in Blackhat last year too. So a simple description of the bug we found. So in Reader X, there's a register entry for enabling or disabling the Reader X sandbox. Interestingly, there's an allow policy that covers this register key. But of course, there's a registry deny access policy denying access specifically for this register key. But the problem is you can bypass the deny access policy by just adding additional backslashes to the registry resource name, such as this one. So what happens is that due to this bug, a sandbox code is able to disable the Reader X sandbox. Services are a large attack surface for a sandbox escape because most of them are runs in a high privilege context and process untrusted data. Two examples of service vulnerabilities are two vulnerabilities we identified in Chrome Flash Broker earlier this year. This is the description of the two bugs. So as you can see, the two service handlers in the Chrome Flash Broker accept a pointer as a first parameter, this one and this one. And that pointer had been fully trusted and the reference inside the service handlers in a call instruction. So if you look at this code, you can easily control the address in the call instruction. With additional research of how to inject code in the broker process, and then leaking the stack address of the broker process back to the sandbox process, we are able to execute arbitrary code in the Chrome Flash Broker process. We will use one of these bugs in our sandbox escape demo later. So for sandbox escape involves exploiting a weakness in a high privilege process. Two prime examples of weaknesses that can lead to a sandbox escape are permissive policies and improper handling of untrusted data. And finally, the sandbox mechanisms themselves are also potential vectors for a sandbox escape.
Okay, we're going to demonstrate a sandbox escape. In this demo, we'll be using 3 different vulnerabilities, 2 for the remote exploit, and 1 escape exploit that we found in Chrome Flash earlier this year. Okay. So in this demo, we'll be using 2 machines. One is the machine that serves the exploit, and the other one is the victim machine. So please focus on, before Mark clicks the exploit, or the URL, which he made a bookmark for the exploit URL. He liked it so much. And please look at this Process Explorer, and you can see that it will open the Flash Broker process, and to visualize a successful exploitation, we are going to spawn. We're going to spawn not 1 but 2 calculators. As you can see, 1 calculator has a integrity level of medium, and that's the one that is spawned by the exploited broker process, and the other one has an integrity level of low. This is spawned by the initially exploited sandbox Flash plugin process. Okay, so to conclude our talk, what have we learned? We learned that sandboxing technologies has made exploitation more expensive for the attacker because they now need an additional sandbox escape vulnerability to fully compromise the system. But we also learned that even though sandboxes have proved to be effective, it is also true that limitations still exist. And users should be aware of this. And lastly, we have concluded that out of the 3 sandbox implementations, PepperFlash is the most restrictive. And we are looking forward to it being the default Flash player in Chrome. So that's it for our talk. Thank you very much. If you have any questions or if you just want to chat, we will be at the IBM booth number 601 from 4:35 p.m. onwards. And if you have some questions now, you can also ask. Thank you.